Good afternoon and welcome to the afternoon session of the International Conference on Innovations and Research in Marine, Electrical and Electronics Engineering. This session will focus on artificial intelligence and soft computing. I'm profusely elated to take an opportunity to introduce our chief guest. Dr. John Paneerselvam is a lecturer in informatics within the School of Informatics, University of Leicester. He received a doctoral degree in the discipline of computing from the University of Derby. He largely focused on energy-efficient data centers and also works in the areas of interdisciplinary analytics, scheduling, and resource management in distributed data centers, Internet of Things, etc. He is an active researcher and have collaborated with several research groups across the globe, Jiangsu University, Tongji University, and Anwu University of China, Satyabama Institute of Science and Technology in India, to name a few. He has generated various forms of research outputs in the field of cloud computing, peer-to-peer computing, Internet of Things, big data analytics, wireless sensor networks, and network security. We are indeed glad to have such an eminent and resourceful personality as a keynote speaker for this track, Artificial Intelligence and Soft Computing. On behalf of the Academy of Maritime Education and Training, deemed to be university, and the Department of Electrical and Electronics Engineering, I would like to welcome you once again, sir. Now, I request Dr. John Paneerselvam to deliver the keynote address.
Yeah, thanks a lot for the warm introduction. So thanks for providing me the opportunity. So I'm glad to be here. So I can make a start when we are ready. Brilliant. So thanks for the opportunity here. So good afternoon to all. I believe you are enjoying the conference so far. So my talk today is basically focusing on energy efficiency in cloud computing. I just wanted to share a part of my recent research output. So we have been working in this domain for about for more than a decade now. So we started off at looking at the energy consumption issues of data centers way back in 2011. So we started to look at various factors affecting the data centers, and we adopted a data-centric approach for addressing the energy conservation at the massive data centers. So this work here is a part of my recent research, and we have been looking at various machine learning, deep learning approaches, and this is just one of them where we attempted to predict the future behaviors of the data centers, the task behaviors of the data centers, and obviously, with the motivation of contributing towards decision making at the data center in an energy efficient way. So, okay. So I'm just struggling with some seasonal flu. I may have some occasional cough. Apologies for that. So today I'm going to briefly introduce my university of Leicester. So I'm a lecturer here in informatics at the School of Informatics within the University of Leicester. And of course, I'll briefly talk about the issues around the sustainable data centers and what we are basically trying to address there, and the motivation of this particular piece of work. And I'm also a bit conscious about time as well, so I'll briefly introduce the working mechanism of one of the models that we developed, which is a forecasting model to predict the future behaviors of these workloads at the data center. So in this model, the idea is to predict the arrival frequency of these jobs at the data center based on their characteristical behavior, so which would basically help us to find the right servers, and task placement, scheduling, etc., depending upon the task priority, and also how the servers behave in an energy efficient way. So I just wanted to introduce this piece of work today. So University of Leicester is a traditional university located within the heart of the city of Leicester. So we are just a little away from London, so maybe an hour drive on road. So very close to London, in fact. So we are ranked 170 in the world by the Times Higher Education, and most of our research are renowned as making a societal impact. In fact, more than 75% of our research is deemed to be making a societal impact. And we have we have our research domain spanning across various societal domain as well. For example, we have a Leicester Space Center. The National Space Center is located at the city of Leicester, and the University of Leicester makes a significant part of it. So we contribute towards satellite building and electronic components that goes into the satellite and things. And also we work closely with various hospitals across the UK as well. So we work on various research projects contributing towards medical analytics with bioinformatics, particularly our School of Informatics. We have a good number of colleagues working with doctors across the UK on various medical related problems. So we are obviously ranked top 25 in the UK, and we are one of the top UK universities known for our research outputs. And this year is obviously our 100th year, of course. So the university was actually opened just after the First World War, 1921 established. So this year we are obviously celebrating our 100th anniversary. So energy issues in cloud computing. So what we have been trying to address over the past years. So as you know, we all use cloud computing for various purposes, and of course nowadays, the distributed nature of cloud has extended and outreached to, for example, into the palms of our hand. For example, we use we connect our mobile devices to the cloud, and we even we're talking about things like fog computing, edge computing, where we utilize the mobile nodes to orchestrate the resources together to form decent computing nodes. And of course, we still use traditional cloud computing despite the outreach of cloud computing and the distributed nature like fog and edge computing. So we still rely on these massive data centers for intense computing tasks. For example, we may only be able to do some lightweight computational tasks in these mobile devices and also in the fog nodes as well. But for intense computing, anything that needs massive server power, we still rely on these cloud data centers. So clouds are still growing. So and there's a recent trend. For example, IT-centric organizations, they are building and hosting their own IT services, which basically means they are building their own data center without having to externally rely on third-party service providers. For example, we as a university, obviously any university, they need IT resources and IT support, and we host our own IT services. We have some in-house data centers which provide services for all of our IT needs. So which means data centers are growing and they are causing this environmental impact as well. So data centers are also addressed as an important source of carbon footprints. Likewise, the automobiles and cars on the road, data centers also pollute the environment. So whatever that we feed in, we feed the servers with electricity, and of course these servers will have to be cooled down as well. So we use cooling mechanisms, and they throw carbon footprints out to the environment. So when we talk about sustainability, there are a few things that needs addressing. So one of the important things is to reduce the input power that we feed into these servers. So this is just a view of a Facebook data center in Sweden. So as you could see, the servers are racked up, maybe just one portion of the data center. So we got loads of servers, and all these servers needs input power. And some of these servers, or in fact most of these servers, run without producing any IT services, which means basically they simply feed in. They are simply fed in with electricity, but they don't produce any IT services. So literally they stay active in maybe in an idle mode, but they don't produce electricity. So we need to spot these idle servers, and possibly we can turn them down. That's one way of reducing the input power consumption, and also consolidating the workloads onto minimal number of servers. So we try to extract maximum utilization from a minimal number of running servers is one of the other strategies. But all of these need some input knowledge. So the service provider, they don't usually gamble with the quality of service. For example, as a user, we always want on-time services. For example, we don't usually wait for our services. If the services are backlogged and if the users experience significant delays in getting their resources, obviously then they will move into a different service provider. So in order to avoid such a scenario, cloud providers always tend to be running these servers in an idle mode, so that when there is an overwhelming volume of incoming services, then these servers can be utilized there because they are readily available at that point. But obviously, the other consequences is increased power consumption and also increasing levels of carbon footprints. So that is what we have been looking at addressing in the past few years. So just a quick forecast to re-emphasize what I've been talking with some statistics. You could see data centers, the green pile, occupies a significant portion here. Almost 21% of the electricity demands comes from these data centers. So roughly they consume about 416 terawatt hours every year, and that is quite massive. It is a massive volume. So when the demand increases, obviously the protection will have to be increasing as well. So when we talk about feeding these data centers in, we need more. We need to find more resources of electricity. So what are the concepts of sustainable data centers? So when we talk about the electricity resources, one of the recent strategies is to feed the data centers with some renewable resources like hydropower, solar power, and wind energy, etc. So, for example, some data centers in China, for example, Baidu Cloud, they've already powered their data centers with wind energy, almost 100% renewable. So that means we don't have to deplete the non-renewable electricity, as we may need to conserve these resources as well. So one way of addressing the input electricity is to find more renewable resources to power in these data centers. And so moving these data centers into the Nordic regions, for example, Sweden, the one that we looked at in the last slide is obviously located in Sweden. As you know, these Nordic countries, they naturally, the outside temperature is going to be fairly low, even fairly lower than in the UK. So, for example, the most of the days in a year, the outside temperature would stay less than 5 degrees in these countries. So moving these data centers into those countries would help in a way that the cooling management, the cooling requirement naturally reduces. For example, when you run your laptop, for example, you can't run the laptop for a continuous 2 days. The laptop would obviously experience more heat, and it would then damage the hardware and things. So when we run these servers for a while, then it's quite important to cool these servers down. So we can use some artificial cooling systems like air conditioning, and that needs input power as well, and also things like water cooling, water-based cooling systems, and all needs input power. So when we host these data centers in these countries where the outside temperature is naturally low, we can reduce our input requirement, the electricity requirements for these cooling management. So that's cooling management that I've been talking about anyway. So, and of course, there are some initiatives like Baidu Cloud and Google Cloud as well. They are reducing their power usage effectiveness. So the power usage effectiveness basically, it tells us how energy efficient a given data center is. A PUE of 1 is very energy efficient, which means for every input power, we don't need an equivalent input power to cool the servers down. a PUE of 2 implies it's not very energy efficient at all. For example, if you feed the servers with certain input power, the same amount of input power is required to cool them down. So the global average was 1.7. It might be better now when I just drafted these slides. So China is obviously pushing for a global, 1.3. And there are some data centers, for example, even Google data center, they are claiming to have reached 1.1 or below. And Facebook data center, when they are located in these Nordic regions where the outside temperature is naturally low, the PUE will be anywhere closer to 1. So even if we feed these data centers with renewable sources, the output, the carbon footprints are still a concern. So we need to, ideally the global strategy will have to be reduce the utilization of these servers, reduce the running duration of these servers, so their corresponding carbon footprints into the environment can be addressed. So that is where we are looking at. So the data center environment, as you may be aware now, a data center comprises massive number of servers, and we host containers or virtual machines in these servers. So when an incoming task arrives, a virtual machine or a container will be deployed in these servers, and the user's requests are actually hosted in these servers. And a data center may have a few thousands of physical servers. The one that we analyzed comprises of more than 12,500 servers, and also we are looking at other Alibaba Cloud, which comprises of more than 16,500 servers. So the total number of servers in our data centers are quite massive. And what we will be looking at is we don't have to run all these 12,500 servers in a data center. So we can run them when they are actually required and turn them off when they don't have to be on all the time. So what how machine learning and AI can help in this context. So what we have been looking at is forecasting the future arrival trend of these servers. Sorry, the incoming workloads. So, for example, if we know the next hour is going to be very busy, for example, if we see an exponential increase in the next 1 hour in terms of the number of workloads coming into the cloud, then we can immediately scale up these running servers, the number of servers, so we can power them on pretty quick. So, and these servers characterize wake-up latency. For example, when you turn your mobile phone, it may be very quick. Within a few seconds, you can access the resources. But when you turn the laptop on, it may be a minute or two before you can access these resources. Likewise, the servers will have their own wake-up latencies as well. It can be a few minutes as well. So that few minutes may also have an impact in the quality of service. For example, think about if you have to wait for 5 minutes for a web page to load. What we would do naturally, users won't be happy and they tend to go for somewhere else. So that's what will happen. I think the world average for a web page to load is 8 seconds. If the web page wouldn't load for within a period of 8 seconds, then obviously the users tend to reload it. So users aren't that patient. So these data centers will have to provide readily available resources. And the resource estimation is another way. So yes, we know what is going to arrive in the next 1 hour, and we should also know how these tasks are going to behave in the data center. So, for example, what level of resources they would consume, what level of CPU they need, how long they would be executing, and what level of memory they need, etc. So we need to look into that behavioral characteristics as well. But cloud workloads are fairly dynamic, so in such a way that they consume different level of CPU. Even similar jobs may consume different levels of resources, and that that imposes various levels of challenges in addressing these task behaviors. So what we have been looking at is analyzing large-scale cloud trace logs, which we obtain from a real life data center. So we have been analyzing trace logs, real world trace logs obtained from Google data center. Google's one is publicly available, so anyone can access it. And recently we are also working on Alibaba Cloud as well. So that is again publicly available. And these are prototypes released for research purposes. And Google released one in 2019. It has abundant, source of knowledge, and of course it needs some intelligent computing as well. So we can analyze these trace logs to get some useful insights for decision making. So just an overview of a cloud workload, how it looks like. So a job usually comprises one to several number of tasks. We have been looking at a job that comprises of more than 2,000, 5,000 number of tasks. So in order to complete this job, all the tasks will have to be completed. For example, this job one has n number of tasks, and in order to complete this job J1, all the n number of tasks will have to be completed. And these jobs can be parallel; they run parallelly, or they can run in a serial fashion, or we may have a combination of parallel and serial tasks. For example, if T1 and T2 are independent, they can be processed simultaneously. But if T2 is dependent on T1, then we need to complete T1 before we can go into T2. So it depends on the internal task dependency and the independent nature of these tasks as well. And in terms of the nature, the resource consuming nature, they can be less resource intensive or they can be more highly resource intensive. So these, the heterogeneity is basically when all these tasks behave differently. So if a job has a combination of more number of parallel and serial tasks, and if they consume highly dynamically in terms of their resource consuming nature, then we have that heterogeneity. So initially, I just wanted to approach the presentation firstly, I wanted to present the knowledge that we extracted out from our descriptive study of this data center, and then I'll talk about the prediction model that we developed. So the data center that we worked on for this particular work is, it is a Google's trace logs. So it has about 650,000 jobs, extracted from 12,500 operating server. So a job profile usually comprises of the submission time, username, and job name, and we have the user profile that includes their resource request levels as well. So the motivation of this particular work is to analyze the impacts of the latency sensitivity of these workloads. So any workload will characterize some latency sensitivity. This latency decides how quickly these workloads will have to be processed. For example, they can be less latency sensitive, or they can be highly latency sensitive. So when the provider sees these two tasks come in at the same time, obviously the priority is to process the highly latency sensitive workloads first thing. So they can be processed quickly, and they can be the output can be delivered to the user within the reasonable time scale. So we want to analyze the distinctive effects of this latency sensitivity. So I previously explained the dynamic and heterogeneous nature of these workloads, and in terms of their resource consumption, for example, the CPU, memory, and the duration. So latency is obviously related to the duration, how long the tasks are executing. So latency decides within which a workload will have to be processed at the data center. And we know, as I said, that particular trace log has 650,000 jobs, within a period of 4 weeks. And all of these tasks and jobs comes with different levels of latency. Sorry, just give me 1 minute. I'll just close the windows. Got outside noise. Sorry about that. So the impacts of latency here. So we wanted to derive the impact of this latency sensitivity on the energy efficiency. So so we wanted to look at a categorization of these workloads in terms of their latency characteristic, and then model the impact of these latency characteristic upon energy efficiency, and how we can go on to build the prediction model. So our strategy is to analyze the latency impact at both the inter and intra job levels. For example, if we take a job as a whole, let's say that this job has about 10 number of tasks. If all these 10 number of tasks are least latency sensitive, then the job is obviously can be deemed as least latency sensitive. And if this job has a combination of least and highly latency sensitive tasks, then we have more challenge. So we wanted to look at this heterogeneous nature as well. So latency can be of different types. The most obvious one is the network latency and the dispatching latency, that obviously directly associated with the communication latency. So when we send, let's say you're uploading some jobs to the cloud, let's say maybe an iCloud, when you try to upload some photos from your iPhone. So the network and dispatching latency determine how quickly you can complete the upload process, right? And this latency is dominated by the quality of the network that we have, any network bottlenecks, any congestion, etc. So that is purely the communication latency, and we were not interested in the communication latency. So we were talking about the in-house computational latency. So after the job arrives at the data center, how the latency affects their processing. That is what we are interested in. And this computational latency determines how quickly the jobs will have to be scheduled after arrival, and how quickly the jobs will have to be processed. For example, we can schedule a task in a virtual machine or a physical server that is less capable, or has some it's not highly efficient. For example, if the server, then these tasks can run longer and can still be completed. But if these tasks will have to be completed very quickly, then we may need more aggressive, more capable servers. So and these servers may complete the tasks within a quick time scale. So depending upon the computational latency characteristics of these servers, it's quite important to determine the servers as well in the data center. And of course, workloads are characterized by various levels of latency, and the latency sensitivity depends on the allowed time scale. So the round trip time, for example, so within that determines within which the job will have to be accommodated and completed after its arrival at the data center. So the taxonomy of latency in this particular trace log was quite explicit, and we have an index for all these tasks and also all these jobs as well, that explicitly defines the taxonomy of latency for these tasks. So that made our job quite simple. So we don't have to label them. So these are pre-labeled in the actual trace log that is provided by Google. So 0, they are least latency sensitive tasks, non-protection tasks. So they can be processed at a later time. So time is not a big constraint here. So then the next level of latency sensitivity comes with the machine interactive workloads. So these machine interactive workloads will have to talk to each other. For example, maybe there is some level of interdependency among these tasks. If task 1 is scheduled in virtual machine 1 and task 2 is scheduled in virtual machine 2, for example, there will be some interaction between virtual machine 1 and virtual machine 2 in order to complete these tasks. And of course, because there are some internal communication involved here, and there is some level of latency. If the communication is not flowing through nicely, then we may have some delays in execution. Then the next level comes in with a level 2, that is real-time machine interactive workloads. So the delay sensitivity here stays at the level of tens of milliseconds. So it is quite sensitive. So we need to schedule these in extremely capable machines. And the highest level of latency sensitivity comes with level 3, and usually they are revenue generating user workloads with the delay sensitivity staying at sub-milliseconds. So they are quite highly latency sensitive. Usually they, revenue generating workloads, for example, stock exchange data and things, or online gaming, for example, so where delays cannot be tolerated. So depending upon the latency sensitivity, usually the service providers can do the scheduling and task management at the workloads. For example, if task 3 is struggling somewhere and it needs better resources, then least latency sensitive jobs can be terminated. For example, level 0 and level 1 possibly can be terminated by the providers in order to accommodate level 3 and level 2 workloads whenever there is a resource scarcity. So that is one of the general strategies of the service providers, to kill and terminate the least latency sensitive workloads in order to accommodate highly latency sensitive tasks in any data center. So we try to quantify the number of tasks in a given day depending upon their latency sensitivity. So this plot here is a 28-day plot, just purely the number of jobs that we received in any given day. As you could see, the most of the jobs that we received in any given day are least latency sensitive. So mostly, almost 40% of the jobs in that data center are least latency sensitive, and of course, 32% comes with level 1, level 2, 29%. So look at level 3 is only 0.63%. So the revenue generating workloads at sub-millisecond level of latency is very insignificant. So only 0.63% in that particular data center. Obviously, I'm not trying to generalize these statistics for across all the data center, but it comes true with most of our study. For example, when we studied the Alibaba cloud as well, we had similar inferences. So that is to say, most of the jobs that are received in that particular data center are least latency sensitive, where time constraint is not a problem. So whenever we have highly latency sensitive workloads, these 38% workloads can be killed and terminated, because delaying these workloads will not have an impact in the quality, but delaying the level 3 workloads will have a significant impact. And so we look at the job terminations. For example, here, this plot tells us how often these jobs are terminated. So there are there are a few different types of terminations, but 2 types are more predominant. So the first one is the kill event, when users or the provider intentionally terminate these tasks, then it is termed as kill event. When these tasks naturally fails, then it is obviously a fail event. So when you look at this plot here, 26% of least latency sensitive jobs are naturally killed, and 47% of level 1 jobs are killed as well. But when you look at the level 3 workloads, only 1.1% are failed, and 1.52% are killed. So the total number of kills, the intended the service provider kills are quite significant with level 0 workloads. As obviously, killing these level 0 workloads will not have an impact on the quality of service, but killing the level 3 workloads will have an impact. So the obvious inference here is, so whenever level 3 workloads are struggling to be accommodated, in order to release more resources for these level 3 workloads, obviously the service provider will kill the level 0 workloads naturally. So that is what we are trying to infer in here. So, and we did the same quantification at the task level as well. And of course, we had similar inferences. For example, 79% of almost 80% of the tasks are least latency sensitive with level 0, and only 0.47% of the tasks comes with level 0 as well. Sorry, level 3. So with the inference are very similar. And also, when you look at the kill event and the fail event as well, it is very similar. And also there's another event at this point as well, so which is an evict event, so which is basically in order to accommodate highly latency sensitive workloads, service provider, rather than killing the least sensitive workloads, they tend to pass these workloads and resume later, so that they don't have to kill them entirely and start from scratch. Instead, they can pause at any given time and resume from where they left at that point. So again, we have similar inferences. So look at this level 3 here. The kill, fail, and evict events are very insignificant because they don't want to they don't want to have an impact of these level 3 in these level 3 workloads. But look at level 0; it's quite significant. So 86% failed, 64% kills, and 74% of evicts. So that is again obvious. In order to accommodate highly latency sensitive workloads, they providers intend to terminate least latency sensitive workloads as they don't have an impact on the quality of service. So the inference that we obtained from these quantification, the initial study, the descriptive study, are jobs naturally they exhibit weekly correlations, whereby during the weekdays we can have an increased number of submissions and the number of jobs decline over the weekend, and no correlation exists among the job and tasks events. They are totally independent. And very low proportion of highly latency sensitive tasks are completed without facing any constraints. And also when they try to accommodate highly latency sensitive workloads, least latency sensitive workloads are always found to be the victims because they are killed and failed most often. So what we intend to do here is a latency wise classification may help. So rather than treating these jobs as a whole, for example, within any window that we are looking at, for let's say we are trying to do some classification and prediction in this 1 hour. So we capture all these tasks within that 1 hour, and we try to do a classification based on their latency sensitivity. And that is to help the resource management, performance optimization, and energy efficiency. So we do some latency aware classification, and we do some prediction from there, and we can implement them in the data center for decision making. So with these inferences, we developed a prediction model. So I just wanted to briefly introduce this prediction model. I'm also conscious of time as well, so I try to go through this pretty quick. And of course, I'll have the list of publications at the very end as well, so where you will be able to find the precise information of these papers. So the motivation of this particular work is to forecast the future arrival trend, as I said before. So what are we expecting in the next 1 hour or next 30 minutes or so, depending upon how long we set the prediction window for. So this forecasting will come from the latency aware classification. So we wanted to do the latency aware classification first. So we classify, or we cluster these workloads into 4 respective groups. For example, level 0, level 1, 2, and 3, depending upon their latency characteristic. And then we do the prediction. So for this initial classification, we used a k-means clustering algorithm. K-means is obviously a traditional clustering algorithm, you may be aware. But we made some improvements in order to accommodate the characteristics of the cloud workload behavior. We made some improvements in the traditional k-means algorithm. And so the output of the k-means algorithm is then fed into a a neural network architecture. So we used a back propagation neural network. So again, the traditional back propagation neural network, we noticed some issues with it. When we try to optimize the learning rate and momentum factor in that neural network architecture. So in order to accommodate again, to make these architectures suitable for our task here, our objective here, to predict the user cloud workloads, we made some improvements there. So I'll briefly talk about those improvements as we move along. So the output of the k-means is fed into the neural network architecture, and we have the prediction based on these initial classification. So the traditional k-means, as you may be aware, it partitions the number of clusters. It partitions the given observation into a number of clusters. Depending upon we can set the number of clusters that we want. It works based on a centroid, which means for every cluster, it assumes a centroid, illustrated by this x factor here, so x value here. So depending upon a distance measure, so if we have an observation coming in, so it measures the, for example, if we have an observation coming in, it measures the distance between that particular observation and each of those centroids in these clusters, and it chooses the closest centroid. So as long as the distance between that centroid and the given observation is the smallest, then it fits that particular observation into that cluster. So that is basically the traditional k-means. But the problem here is determining the total number of clusters that we want is quite challenging, and also the determining the centroid is also quite challenging as well. So the number of clusters are often need to be explicitly specified in this traditional k-means, and we witnessed determining the k value. The number of clusters basically is quite challenging, and that wouldn't fit our objective as well. So even though we know the classification that we are looking at is basically 4, when we talk about the latency sensitivity levels 0 through to 3, but we also wanted to increase the number of clusters, because increasing the number of clusters will give us more precision, more accuracy. So we try to improve the characteristics of the traditional k-means algorithm, or in other words, we wanted to make this traditional k-means algorithm to be more suitable for our classification objective. So basically, the objective is to eliminate the complexity when determining this k value, the total number of clusters that we want, and the cluster centroid as well, the center point of these clusters. So we wanted to incorporate the the behavioral characteristics of these workloads, and the latency sensitivity will have to be carefully captured by the classification algorithm. So initial classification helped us to explicitly define the total number of clusters that we want as an output, and that makes us to achieve a precise clustering. So then the back propagation algorithm, so the back propagation neural networks. So neural networks, as you may be aware, it has an input layer, an output layer, and one or more number of hidden layers. So the signals that are received from the previous layer are are multiplied by a bias factor. So every node, for example, this green node is located in a hidden layer, and gx is the output function of that particular node. And AI1, AI2, AIN are the signals coming from the previous hidden layer, or the input layer, for example. And these signals AI1, then, for example, when received by this node, it multiplies that particular signal with a weight function, what we call as bias of that particular node, and then that will be treated by an activation function, and all these signals are then summed up together and generated as an output for that particular node. So AI1 and AI2 and AIN, for example. After treating with the bias and activation function, the output will be generated by adding these signals together. And the same operation goes along if we have one or more number of hidden layers. Every node, when receiving the signals, will do the same. So treats them with the bias and activation function and produces the output. But back propagation neural network. So when we have the initial architecture, it is quite important to revisit the architecture and do some adjustments in the bias value, the weight value, the activation function, etc., in order to fine-tune the neural networks to get the maximum optimization possible. So back propagation architecture uses a negative feedback. It revisits in the backward fashion, and then it changes the weights, the bias, activation function, etc., in each of those nodes in the previous hidden layer. So it back propagates basically to do these adjustments, and that is why it has its name, back propagation neural network. So it has a better ability to work with non-linear relationship data. So, but the traditional back propagation neural network has some problem. So we experienced some issues when we try to optimize the learning rate and the momentum. Learning rate and momentum are quite important in any neural network architecture. So as they decide the position and accuracy, and also the time within which the architecture can converge. So for example, if the learning rate is too large, then we cannot get a reliable position. On the other hand, if it is too slow, then the network will not converge and the output would take too long. So we want to balance the trade-off between learning rate and momentum in any neural network architecture. And that is particularly true when we deal with large-scale data, as in our case, we are dealing with within the with the big data, obtained from these Google trace logs. So we try to modify the traditional back propagating neural network architecture by the modification comes in the way that how we actually optimize the learning rate. So when we do the fine tuning, the values of fine tuning usually they comes from an empirical study. Not we don't usually do it from a probabilistic approach. So it comes from an empirical approach. So usually the fine tuning is derived from this mean squared error factor. So the mean squared error is obviously computed between the difference between the actual value and the predicted value. If it is if the MSE value is negative, then the learning rate is usually multiplied by a factor more than 2, higher than 2. If it is positive, then the MSE value is multiplied by a factor that is between possibly 0 and 1 in our particular approach. So rather than adopting simply adopting a random approach, we adopted the fine tuning of the learning rate and and the adjustments of these weight factors derived from this mean squared error value. So what we achieve from that one is from this approach is the mean square error is avoided from a continuously decreasing trend, and avoiding the local minima during the convergence is quite important. So that is something that we wish to achieve in this particular model. So also this helps to increase the learning rate as well. So so we try to increase the precision of the model. At the same time, the convergence of the model is not too long. So we can obtain the global minimum as quickly as possible without affecting the learning rate of the model. So obviously, as I mentioned earlier, the improved k-means algorithm is used to initially cluster the workloads depending upon their latency characteristic, and then under different time periods, and the output of that particular clustering algorithm is fed into the modified back propagation neural network, and we saw a good satisfactory predictive effect. So the prediction is driven for different clusters that we adopted. So every cluster will be treated differently, and the fine tuning of the back propagation neural network will be based on how these clusters are actually initially obtained. So for example, the fine tuning in cluster 1 may be different, and fine tuning in cluster 2 may be different. And of course, their learning rate and the convergence may be different as well. So it's basically incorporating the characteristics of these workload behaviors and approaching the fine tuning of the neural network architecture based on that. So I won't keep you longer. So we also did some experiments to evaluate the prediction performance of this model, and we compared the prediction output with some existing traditional classical models as well. So for example, the naive classifier hidden Markov's model has been traditionally used for this purpose, and we initially developed a similar back propagation neural network architecture with optimized learning rate principle, and and this one, the purple line represents the recent one that I've talked about today. So obviously we see an improved performance, and our recent model outperformed the classical models and also our previous work as well. And we did a comparison between, without doing the initial classification, the clustering based on the latency sensitivity, and also after the impacts of the prediction after, doing the latency-wise clustering. So the red bar here represents the one that we achieved after the latency-wise clustering. Obviously, it achieved a better accuracy. So for CPU-intensive workloads, we wanted to, do the performance evaluation, because memory-intensive workloads and CPU-intensive workloads, they can come with various latency characteristics. And again, we saw similar performance. Our recent, this combo model with improved k-means and improved back propagation neural network obviously outperformed the other models. And of course, it also, the initial clustering also has an impact on for all the levels of latency, sensitive workloads from 0 through to 1. So what we finally infer here is obviously the initial clustering and the latency characteristics of these workloads are quite important, and capturing these latency characteristics into the prediction model and into the decision making. For example, an AI-driven decision making system, support system in cloud data centers, or making a real world impact. So that's the end of the talk today. So I think I've ran a little longer. Sorry about that. So I've got the list of publications here. So this list basically, extends. Just wanted to list down of all the outputs that we generated in the past few years, and we have some reputed publications of our research outputs in for example, fused generation computer systems, a few IEEE transactions, etc. So yeah, so and also we if you wish to explore more about the model that I talked about today, is you can explore this particular paper, the third one in the list here, the latency based analytic approach to forecast cloud workload trend. So that is published in the IEEE Transactions on Sustainable Computing in 2019. And also we developed another prediction model. So if I have a chance in another occasion, I would possibly talk about it. So basically the GRU, it's another trim of neural network basically. So and we incorporated the behaviors in the age of 5G as well. So you're welcome to read through these papers if you're interested. And any feedback, any comments, would also be graciously received. So so I'm stopping at this point, and I'm happy to take on any questions at this point if you have any, please.
Thank you, sir, for illuminating the gathering with your elaborate speech on data centers, data-driven approaches, neural networks, and others.